Industry skills, practical knowledge, real-world impact. This is SimpleGyan.
A jet engine spins at thousands of revolutions per minute. A turbine blade faces extreme heat, vibration, centrifugal force, and repeated stress cycles. To the naked eye, the metal looks perfect. No visible damage, no broken edge, no obvious crack. But deep inside the surface, a microscopic fatigue crack may have already begun. It may be thinner than a human hair. It may be only a few microns wide. But in aerospace engineering, that tiny crack can become the starting point of catastrophic failure. So how do engineers find damage that eyes cannot see? They do not cut the metal open. They do not destroy the part. They do not guess. They use physics, they use electricity, they use magnetism. They use one of the most powerful non-destructive testing methods in modern aerospace maintenance, eddy current testing. This is the story of how electromagnetic induction helps detect microscopic fatigue cracks in aerospace alloys before they become disasters. Part 1. Why aerospace alloys fail. Aircraft components are built from advanced materials. Aluminum alloys are used in fuselage skins and wing structures. Titanium alloys are used in engine parts, fasteners, and high-strength components. Nickel-based superalloys are used in turbine blades and hot-section engine parts. These materials are strong, lightweight, and heat-resistant, but even the strongest alloy has one enemy: fatigue. Fatigue failure does not usually happen because of one big overload. It happens because of repeated loading and unloading, every takeoff, every landing, every engine cycle, every vibration, every temperature change. The metal expands, contracts, bends, and vibrates again and again. At first, nothing seems wrong, but at the microscopic level, small defects begin to grow. A tiny discontinuity near a hole, edge, weld, rivet, or surface scratch can become a crack initiation point. Once a crack begins, it can grow silently with every stress cycle. This is why aerospace inspection is not optional. It is a critical part of aircraft safety. The challenge is simple, but extremely difficult. Find the crack before it becomes dangerous. Part 2. What is non-destructive testing? In normal destructive testing, a sample is cut, pulled, bent, or broken to measure its strength. But aerospace parts are expensive and safety critical. You cannot cut open every turbine blade. You cannot destroy every wheel hub. You cannot break every aircraft panel to check if it is safe. That is why engineers use non-destructive testing, or NDT. NDT means inspecting a material without damaging it. Common NDT methods include radiography, which uses X-rays, ultrasonic testing, which uses sound waves, magnetic particle testing, used for ferromagnetic materials, dye penetrant testing, used for surface cracks, and eddy current testing, which uses electromagnetic induction. Among these methods, eddy current testing is especially powerful for detecting surface and near-surface cracks in conductive materials, and most aerospace alloys are conductive. That makes eddy current testing a major tool in aircraft inspection. Part 3. The science behind eddy currents. To understand eddy current testing, we need to go back to basic electromagnetism. When electric current flows through a coil, it creates a magnetic field. If the current is alternating current, the magnetic field also changes continuously. Now place this coil near a conductive metal surface. The changing magnetic field enters the metal. According to Faraday's law of electromagnetic induction, a changing magnetic field induces electric currents in a conductor. These induced currents flow in circular loops inside the metal. These circular currents are called eddy currents. They are named after swirling eddies in water. In a perfect, crack-free metal, eddy currents flow smoothly. But if there is a crack, corrosion, void, or material change, the current path is disturbed. The crack acts like a barrier. The eddy currents must bend, concentrate, weaken, or change direction. This disturbance changes the electrical behavior of the inspection coil. And this is where the magic happens. The testing instrument does not directly see the crack. It detects changes in coil impedance. Impedance is the opposition to alternating current. It includes resistance and reactance. When eddy currents change, the magnetic interaction between the coil and the metal changes. This changes the coil's impedance. The instrument measures this change and displays it as a signal. To a trained inspector, that signal can reveal a microscopic fatigue crack. Part 4. Maxwell's equations to aircraft maintenance. Eddy current testing is not guesswork. It is practical engineering based on Maxwell's equations. Maxwell's equations describe how electric and magnetic fields behave. In simple terms, a changing electric field can create a magnetic field. A changing magnetic field can create an electric field. And when these fields interact with conductive material, eddy currents are formed. In the inspection world, this becomes a powerful tool. If the metal is uniform, the signal remains stable. If a crack is present, the signal changes. So what began as electromagnetic theory becomes a practical maintenance method. It helps decide whether an aircraft part can remain in service or must be repaired, replaced, or further inspected. This is one of the most beautiful examples of engineering. Invisible physics protecting visible machines. Part 5. Why cracks change. Eddy current signals. Imagine eddy currents flowing through the surface of a turbine disc or aircraft skin. The currents form small loops near the probe. Now place a microscopic crack in that path. The crack is usually filled with air or oxide. Compared to metal, it has extremely poor electrical conductivity, so the eddy current cannot pass through it easily. Instead, the current path becomes distorted. This distortion changes three important things. First, the current density changes. Second, the magnetic field produced by the eddy currents changes. Third, the coil impedance changes. This is detected by the instrument. The crack may be very small, but because it interrupts the current path, it creates a measurable electromagnetic signature. This is why eddy current testing is excellent for surface breaking cracks. Fatigue cracks often start at the surface, especially around fastener holes, sharp corners, blade roots, and high-stress areas. That makes eddy current testing ideal for aerospace fatigue inspection. Part 6. Skin depth. How deep can eddy current testing see? Eddy currents do not penetrate equally through the whole metal. They are strongest near the surface and become weaker with depth. This is called the skin effect. The effective depth of penetration is known as skin depth. Skin depth depends mainly on three factors: frequency, electrical conductivity, and magnetic permeability. Higher frequency gives shallow penetration. Lower frequency gives deeper penetration. For detecting very small surface cracks, engineers use higher frequencies because they produce strong surface sensitivity. For deeper defects, lower frequencies may be used. But there is always a balance. If the frequency is too high, the test becomes sensitive only to the surface. If the frequency is too low, small surface cracks may become harder to detect. This is why eddy current inspection is both science and skill. The engineer must select the right probe, frequency, sensitivity, and scanning method. Aerospace inspection is not just pressing a button. It requires understanding the material, the component geometry, the crack orientation, and the inspection objective. Part 7. Aerospace alloys and eddy current response. Different aerospace alloys respond differently to eddy current testing. Aluminum alloys have high electrical conductivity. They are commonly used in aircraft skins, frames, and structural panels. Because aluminum conducts electricity well, eddy currents are easily generated. This makes eddy current testing very useful for detecting cracks around rivet holes and fasteners. Titanium alloys are lighter than steel and very strong, but titanium has lower electrical conductivity than aluminum. This affects eddy current penetration and signal strength. Nickel-based superalloys are used in turbine engines because they can survive extreme temperatures. These alloys are complex. Their conductivity, heat treatment, grain structure, and surface coating can influence eddy current signals, so inspectors must calibrate the equipment carefully. A signal from an aluminum wing panel will not look the same as a signal from a titanium blade root or nickel superalloy turbine disc. The material matters, the geometry matters, the heat treatment matters, the surface condition matters. This is why aerospace eddy current testing requires deep material knowledge. Part 8. The equipment used in eddy current testing. A typical eddy current testing system has three main parts: the instrument, the probe, and the calibration standard. The instrument generates the alternating current, processes the signal, and displays the results. The probe contains one or more coils. Different probes are designed for different applications. Surface probes inspect flat or curved surfaces. Pencil probes inspect small areas and tight spaces. Bolt hole probes inspect holes where fatigue cracks often begin. Array probes use multiple coils to scan larger areas faster and create detailed inspection maps. The calibration standard is extremely important. It is usually made from the same or similar material as the part being inspected. It contains artificial defects, such as notches with known depth and length. Before inspecting the real component, the technician scans the calibration standard. This sets the sensitivity of the equipment. Without calibration, the signal has no reliable meaning. In aerospace inspection, calibration is not a formality, it is the foundation of trust. Part 9. How inspectors detect microscopic fatigue cracks. Now let us follow a real inspection process. A technician receives an aircraft component for eddy current testing. First, the surface is cleaned. Dirt, oil, paint thickness, oxidation, and surface roughness can affect the signal. Next, the technician studies the inspection area. Where is the highest stress? Where are cracks most likely to begin? Are there holes, edges, slots, blade roots, or welded areas? Then the probe is selected. If the inspection is for surface cracks, a high-frequency surface probe may be used. If the inspection is inside a fastener hole, a rotating bolt hole probe may be used. If the inspection is over a large area, an eddy current array probe may be used. Next comes calibration. The technician scans known reference notches. The instrument response is adjusted until the defect signals are clear and repeatable. Then the real scan begins. The probe moves slowly across the inspection surface. The technician watches the impedance plane display. A normal area produces a stable trace, but when the probe crosses a crack, the signal shifts. The direction, amplitude, and phase of the signal help identify whether it is a crack, lift-off change, geometry effect, or material variation. This is where human expertise becomes important. Not every signal is a crack. A change in probe angle can create noise. A coating thickness change can affect lift-off. A sharp edge can produce a geometry signal. A material property change can look like a flaw. So the inspector must separate real defects from false indications. In critical aerospace work, indications may be confirmed using another method or a second inspection technique. Safety depends on accuracy. The heart of eddy current interpretation is the impedance plane. Instead of showing a simple yes or no result, eddy current instruments display signal movement. The horizontal and vertical directions represent changes in coil impedance. Different conditions create different signal patterns. A surface crack may move the signal in one direction. Liftoff may move it in another direction. Conductivity changes may create another pattern. By adjusting phase rotation, gain, filtering, and frequency, the technician can separate the crack signal from unwanted noise. This is one of the biggest advantages of eddy current testing. It does not only detect a disturbance, it helps classify the type of disturbance. For example, in aircraft maintenance, inspectors often need to distinguish between a real fatigue crack, a scratch, a surface coating variation, a fastener edge effect, a conductivity change from heat treatment, or probe liftoff caused by uneven contact. The impedance plane helps turn a complex electromagnetic response into meaningful inspection information. Part 11. Eddy current testing around fastener holes. One of the most important aerospace applications of eddy current testing is fastener hole inspection. Aircraft structures contain thousands of rivets, bolts, and fasteners. These holes are stress concentration points. When a hole is drilled into a metal sheet or structural member, the stress around the hole becomes higher than in the surrounding material. Under repeated loading, fatigue cracks often begin at the edge of the hole. These cracks can grow radially outward. The problem is that many of these cracks are hidden under fastener heads or inside holes. Eddy current testing is extremely useful here. In some inspections, the fastener may remain installed. In more detailed inspections, the fastener is removed and a rotating probe is inserted into the hole. The probe spins inside the hole while scanning the inner wall. If a crack is present, the eddy current flow is interrupted and a clear signal appears. This method can detect very small cracks before they become visible on the outer surface. For aircraft life extension programs, fastener hole eddy current inspection is a critical technology. It helps older aircraft remain safe by identifying fatigue damage early. Part 12. Eddy current testing in jet engines. Jet engines are among the most demanding machines ever built. Inside the engine, components face high temperature, high rotational speed, high vibration, high pressure, and repeated thermal cycles. A turbine disc, compressor blade, or blade root can experience enormous stress. If a crack forms in one of these components, the consequences can be serious. That is why eddy current testing is widely used in engine maintenance. Inspectors check blade roots, dovetail slots, disc bores, cooling holes, and surface regions exposed to high stress. In some cases, eddy current testing is used during manufacturing. In other cases, it is used during scheduled maintenance. The goal is always the same: detect cracks early, remove damaged parts, prevent failure in service. In aerospace, the cost of inspection is small compared to the cost of failure. Part 13. Advantages of eddy current testing. Eddy current testing has several major advantages. First, it is non-destructive. The component remains usable after inspection. Second, it is highly sensitive to small surface cracks. Third, it gives instant results. Fourth, it can be automated. Fifth, it works through thin coatings in many applications depending on the setup. Sixth, it requires access to only one side of the component. This is very useful in aircraft structures, where the opposite side may be hidden or difficult to reach. Eddy current testing is also fast and portable. A technician can carry equipment into a hangar and inspect aircraft parts without removing large sections of the structure. For aerospace maintenance, this saves time, cost, and downtime. Part 14. Limitations and challenges. But eddy current testing is not perfect. It works only on electrically conductive materials. It is most sensitive to surface and near-surface defects. Deep internal flaws are better detected by ultrasonic or radiographic methods. Geometry can also create confusing signals. Edges, holes, curves, and thickness changes can affect eddy current flow. Surface coatings and probe liftoff can reduce sensitivity. Material variations can also create signal changes that look like defects. That is why inspector training is critical. A powerful instrument is not enough. The inspector must understand electromagnetism, material behavior, crack orientation, probe design, frequency selection, signal interpretation, and aerospace inspection procedures. In safety-critical industries, technology and human expertise must work together. Part 15. Eddy current array, the modern upgrade. Traditional eddy current testing uses a single coil or a small coil arrangement, but modern aerospace inspection increasingly uses eddy current array testing. An eddy current array probe contains multiple coils arranged in a pattern. Instead of scanning one small point at a time, the array can scan a wider area. This produces faster coverage and better imaging. The data can be displayed as a color-coded map. Crack indications become easier to locate and record. Eddy current array is especially useful for complex components, aircraft skins, lap joints, and areas where repeatability is important. It reduces inspection time and improves documentation. As aircraft become more advanced, inspection technology must also become more advanced. Eddy current array is part of that evolution. Part 16. From detection to decision. Detecting a crack is only the beginning. After an indication is found, engineers must decide what to do next. Is the crack acceptable? Does it exceed the maintenance limit? Can the part be repaired? Must it be replaced? Is further inspection required? Aerospace inspection follows strict acceptance criteria. The decision is based on component type, crack size, location, stress level, operating history, and safety regulations. Sometimes a tiny crack means immediate rejection. Sometimes a part may be monitored under a controlled inspection program, but no decision is taken casually. Every inspection result becomes part of the safety chain, from technician to engineer, from maintenance team to flight crew, from physics to passenger safety. Conclusion. Eddy current testing is a perfect example of engineering intelligence. It does not break the part. It does not rely on visible damage. It uses invisible electromagnetic fields to reveal invisible cracks. A small coil creates a magnetic field. The magnetic field induces eddy currents. The eddy currents interact with the metal. A microscopic crack disturbs the current path. The instrument detects the impedance change, and an inspector interprets the signal. This is how Maxwell's equations become aircraft safety. This is how maintenance teams detect fatigue cracks before disaster. This is how aerospace alloys are trusted under extreme stress. Because in aviation, the smallest crack can have the biggest consequence. And sometimes the difference between safe flight and structural failure is not what we can see, but what electromagnetic induction can reveal. Eddy current testing, invisible physics, visible safety. If you found this engineering breakdown useful, subscribe to SimpleGyan for more deep technical documentaries on industrial science, manufacturing, and engineering systems.